Hi, thank you for joining my talk on using Benchtop NMR Spectroscopy for the quantification of cannabinoids. My name is Matt Leclerc, and I'm a senior application chemist at Nanalysis. Nanalysis is a global leader in magnetic resonance research with over 80 employees and over 1,000 customers worldwide. We manufacture high-performance benchtop nuclear magnetic resonance spectrometers, which I'll introduce to you today. The field strength of an NMR spectrometer is extremely important, as highlighted in this figure. Traditional high field and high resolution spectrometers require large amounts of cryogen to cool the magnet to superconducting temperatures, a dedicated room due to the size of the instrument, as well as expert staff for upkeep and routine maintenance. Conversely, low field and low resolution instruments, commonly referred to as relaxometers, continue to be used in various industries such as oil and gas for routine analyses. Our instruments lie somewhere in the middle, as low field but high resolution instruments. Some of the features of our main spectrometer, the NMR Ready 60, are highlighted below. In short, it features a 1.4 Tesla hybrid Hallback neodymium iron boron magnet operating at a proton frequency of 60 MHz. It requires no cryogens and has no moving parts. It includes automated and manual magnet shimming procedures. The magnetic, electronics, and computer are all included in one compact and portable enclosure, weighing only 55 pounds. The instrument uses standard 5mm NMR tubes and exports data files in formats compatible with most third-party software. One of the most powerful ways in which NMR is used is for structural elucidation. In other words, it provides insight into the structure of a molecule, both in terms of connectivity and through space interactions. This allows us to confirm molecular structures or to piece together the outcome of a reaction or a chemical process. NMR can also be used to monitor reactions in progress, either to determine when a reaction is complete or to identify the formation of byproducts or reaction intermediates, allowing us to better understand the mechanisms governing reactions. More recently, there has been a big push in the community towards the development of quantitative NMR or QNMR. This technique allows us to take advantage of NMR to determine the purity of a sample or to quantify specific components in a mixture. QNMR has been steadily gaining acceptance in both analytical and industrial laboratories. Before I give you a few examples of QNMR at work, I'd like to briefly introduce some key concepts required to fully understand this technique. Firstly, it's important to understand that one of the key advantages NMR holds over other techniques is that it's inherently quantitative. What this means is that the integration area for each signal is directly proportional to the number of nuclei giving rise to that signal. Because of this, calibration curves and specific calibration standards of the sample of interest are not required for quantification, unlike chromatographic techniques. By using the general formula shown here, the compound of interest can be quantified. However, before we proceed to a QNMR experiment, a few key things must be ensured. First, while specific standards are not required, we do still require the use of a calibrant of known purity, to which we will compare the integration areas of the component of interest. These can be internal or, less commonly, external, and it's important that the calibrant's NMR signal does not overlap with any of the signals of interest. In addition, the calibrant must be chemically inert and be completely soluble in the solvent mixture of choice for the analysis. The calibrant should not be hygroscopic or volatile and must be accurately weighed. Finally, a sufficiently long relaxation delay must be used to ensure that all quantifiable components have had the time to relax in between pulses. This can be done by measuring the T1 times of the components of interest and setting the delay to 5 to 7 times that value. It's easy to determine T1 times using the NMR Ready 60 platform, as shown in these screenshots. A few key parameters are used when preparing the experiment, and the software automatically provides the user with a T1 time after the experiment, shown to be 4.1 seconds in the example. The first QNMR example I'd like to share is taken from one of our published sample experiments, and it touches upon determining the purity of commercial compounds, which is a great undergraduate experiment. The procedure is simple. Both the sample and internal calibrant are accurately weighed into the same vial. These are then dissolved in either DMSO-D6 or deuterated chloroform and mixed thoroughly. The sample is transferred to an NMR tube and placed in the spectrometer. The proton spectrum is recorded in triplicate. The purity is determined by integrating the signals for both the calibrant and the sample. These values are input into the general equation I introduced earlier, and the purity is automatically calculated using a spreadsheet. Here is an example of a proton spectrum acquired in this QNMR experiment for 4-hydroxypropiophenone, or 4-HPP, the structure of which is also shown. In this spectrum, the signal of the internal calibrant, maleic acid in this case, was integrated and its assigned value was set to 100. The signal appearing at 1.05 ppm, belonging to the methyl group in the molecule, was chosen for quantification and also integrated. These values were input into the spreadsheet prepared by Polly and coworkers, and a purity of 97.94% was calculated. The results from various commercial compounds are shown in this table. Note that the average of triplicate runs is included here. As you can see, the purities we have calculated on our 60 MHz instrument match very closely to both those obtained on a traditional high-field 400 MHz instrument and those provided by the manufacturer on their labels. More recently still, the pharmaceutical industry has started adopting QNMR for drug assays. Compared to other methods, QNMR does not require the same degree of experimental optimization as typical chromatography techniques. It's also a non-destructive technique, meaning the sample can either be recovered or tested multiple times. Additionally, as we've discussed, NMR is an inherently quantitative technique. For my second example, I'd like to touch upon the analysis of apotadalafil, or as it is most known, Cialis. This experiment involves determining the purity of tadalafil in both apotadalafil and Cialis. Firstly, a proton spectrum of pure tadalafil with dimethyl terephthalate, DMT, the internal calibrant, is acquired in deuterated DMSO using the sample preparation and acquisition parameters detailed on the right. While DMT only shows us one signal, indicated by the red circle, tadalafil provides us with many more. However, the one used specifically for quantification is shown by the green circle. Using QNMR and the same general equation as before, the purity of the pure tadalafil reference compound was assessed to be 99.7%, matching more or less exactly the purity reported by the manufacturer. Using the sample preparation method described on the left, 2 additional samples were prepared, one for Cialis and the other for apotadalafil. The proton spectra were required, and on the right, you can see them overlaid along with the reference sample from the previous slide. As you can see, the excipient used in the Cialis and apotadalafil products adds several more signals to the spectra. However, the signals for the internal calibrant and the sample's proton used for quantification are still very well resolved and can easily be integrated. Using the same general equation as before, we were able to calculate the average mass of tadalafil per Cialis tablet, and as you can see in this table, these match extremely well to those indicated by the supplier. The same holds true for apotadalafil. The results of this analysis are summarized in this table, and also match the values provided by the manufacturer very closely. As you can see, using QNMR for drug analysis has several advantages. The acquisitions only take a few minutes. The data evaluation is straightforward, as the integration areas are directly proportional to the number of nuclei giving rise to the signal. In addition, once the method has been developed and validated, the analyses can be done and processed even more quickly, and a highly trained expert is not required to perform these accurately. Finally, we can build off of these last 2 QNMR examples and see how this can be applied to testing for cannabinoids using Benchtop NMR. As with the previous examples, several advantages of Benchtop NMR over traditionally used HPLC analysis include no need for certified reference standards, no requirements for routine maintenance or highly trained operators, no expensive chromatography columns. Since HPLC is the most commonly used analytical technique for the quantification of cannabinoids, we wanted to see how our own results compared. I'll show you this on the following slides. So far, we've done some work on oil concentrates, flour, and trim. The sample preparation differs slightly between these, but the general approach is exactly the same. For oils, approximately 60 milligrams of the sample is dissolved in deuterated chloroform, and a known amount of a stock solution containing the internal calibrant is added to the oil solution. For this work, our internal calibrant of choice was 1,4-dinitrobenzene, or DNB. Then, the mixture is stirred well and transferred to an NMR tube and analyzed. It's that simple. For flour and trim, the sample is first ground into a fine powder, then suspended in deuterated chloroform, and a known amount of stock solution containing the internal calibrant is added. Then, this mixture is sonicated for 10 minutes, vortexed for 30 seconds, and either centrifuged or filtered. We chose to use a syringe filter for this. We found that we extract approximately 95% of cannabinoids after one extraction, but we do a second one to ensure approximately 99% of cannabinoids are extracted in total. Then, the solution is concentrated and transferred to an NMR tube for analysis. On this slide, I'm showing two proton spectra acquired on our instrument for oil concentrates. The one on the left represents an oil that's very high in THC content, and the one on the right represents an oil that's very high in CBD content. The sample preparation was performed exactly as described on the previous slide. The regions of interest, which we can use for quantification, are highlighted for each molecule. As you can see, these signals are very well resolved and are conveniently located in an area away from the more complex aliphatic region, which tends to be dominated by the signals from the carrier, or the oil. We can also analyze somewhat more complex oils, which contain mixtures of both THC and CBD. As you can see, the spectrum contains additional signals in this case, and there is some amount of overlap between the THC and CBD signals. However, some of the signals are still well resolved, and those we use for quantification are again highlighted. Using the same familiar equation on the right, we were able to calculate the THC and CBD content by weight percent for several different samples. Here, I'm showing the average of triplicate runs using QNMR. As you can see, the RSD values are small, even in the oils where a mixture of both THC and CBD are used. The concentrations of CBD in sample 1 and THC in sample 2 were below the limits of detection for our instrument. But this makes sense, since these oils were specifically chosen to only contain one of the two cannabinoids. Since HPLC remains the most widely used method for cannabinoids testing, we analyzed these same samples using HPLC to see how our results compared. As you can see, they match quite closely. We've determined that the limit of quantification, specifically in weight percent, is approximately 5% for THC and 3% for CBD under these conditions. Additionally, we suspect that the presence of delta-8 THC potentially explains the larger THC content observed for sample 3 by NMR as compared to HPLC. This is still something we're continuing to explore, but we've been quite encouraged by these results and believe that Benchtop NMR is a great complement to HPLC in a testing environment. To summarize, I've shown you that Benchtop NMR has proven to be an effective tool in the rapid determination of THC and CBD content. Because of NMR's extremely powerful structural elucidation capabilities, it is a great tool for the analysis of organic compounds, such as terpenes. However, because benchtop instruments operate at a lower magnetic field strength, signal overlap is more prominent for these analyses. Thankfully, powerful software, such as NMR Solutions, for example, has proven to be an invaluable asset for spectral deconvolution, including at the benchtop level. We believe that by utilizing spectra collected for pure terpenes, it might be possible to utilize software to analyze more complex terpene and cannabinoid mixtures in commercial products. I hope you found this presentation helpful, and I hope you learned a little about our company, Benchtop NMR, as well as how it can be used for quantifying THC and CBD. This type of work is always ongoing in our lab, and we hope to continue refining our methods and continue doing work in this space. We're always looking for collaborators or for someone in the industry to help us better understand what the industry actually needs. If you have absolutely any questions about the work I've presented here, please feel free to reach out to us at any time. Have a great day and enjoy the rest of the webinars.